In this video, we're going to switch gears and take a look at the volume of a solid of revolution, but this time using the Washard method. Now, in this video, we'll only talk about horizontal axes of revolution, and then another video we'll work with vertical axes of revolution. So, as usual, right, if we have the region in front of us and we're given the region, it makes our lives a little easier. However, we don't have that here, right? So I thought we would start with just understanding what the picture looks like before we get into the volume, right? So let's take a quick little sketch, right? 2x squared plus 3, right? If you're not really quite sure exactly how to draw this, I don't know that I would just start drawing the graphs first. I actually would find the points of intersection first. So let's find out, where does 2x squared plus 3 equal 3x plus 3, right? So we know kind of where this region begins and ends. So I think if we just move everything over, it makes our life easier here. 2x squared minus 3x, and then look at that, 3's will eliminate from the problem. So here we are, 2x squared minus 3x equals 0. Let's factor that real quick. Take an x out. All right. So it looks like we have points of intersection at 0 and 3/2. That's important to keep that in mind, because what I think I would do is when I draw these curves, I think I would really start with those two numbers, substituting those in for x, right? So let's do that. If I go and I throw 0 in here to f, right? F of 0 is 3. And if I put 3/2 in there, let's just do that math real quick. 2 times 3/2 squared plus 3, not really convenient. 2 times 9/4 plus 3. So what is that? 9/2 plus 3. So 15 over 2, 7.5, right? Okay, fine. So here's 1, here's 2. Let's call that 3/2. So we'll just say somewhere in this region, right? What's more important is, how do I draw this thing, right? Well, it's a parabola. So I can draw something that looks quadratic. That should do the trick. Now this one's a lot simpler, right? 3x plus 3. So now we're talking about a line whose y-intercept is 3, 4, 5, 6 over 1. So I can already see this, how this is trending, right? And we can see that the line is going to be on top of the parabola. But at least now we have an idea of exactly what region they're talking about, which is really right in there. All right, all that to say, what are we doing? Well, it says, let's get an expression here, an integral expression that will help us find the volume of the solid we get when we revolve that region around the x-axis. So unlike the disk method, look at all that vacant space between this region and that axis, right? When we revolve this thing, that's what tells me I need a washer method. So on that note, let's get rid of all these little dots here, right? The big concern for us is, what is the outer radius and what is the inner radius? So we're going to need 2 this time. So we're going to call uppercase R the outer radius, and we're going to call lowercase r the inner. Now, what does that mean? What that means is, if this is our axis of revolution right here, right, which function is further away from that axis? So you can see it's the line, right? So that means the line, let's go use blue here, right? The line is going to be the outer radius, right? And the curve is going to be the inner radius, right? The parabola. So that helps inform our decision making when we set up our integrand. So it's very similar to the disk method. The only difference really is that when we go to set this up, right, we still have the pi because it's still cylindrical in nature, right? You can see where we begin and end because we found those intersection points, 0 to 3/2, right? We know it's going to be in terms of x because it's a horizontal axis of revolution. So it's going to be a dx out here, right? But now the only change from washer, right, or from disk to washer, is that there's 2 functions to account for. So we always work with the outer one first, and we subtract the inner one next, and that's it. So we know the outer one was really g of x, the line. So we're going to take that one, and we're going to square it, and we're going to subtract the inner radius, right, which was the parabola. In this case, it was f. And there you go. That's all there is to it. Now, had we rotated this around, let's say, a line up here, well, that would change a couple things, and that's what we're going to look at next. So let's kind of circle that. All right, and let's go to part B, right? Same region, but now let's say we revolve it around the line y equals -1, right? So -1's down here, right? So the outer versus inner is still the same, right? If I drew -1 in down here, right? The outer radius is still the line. The line's still farther away from the actual axis of revolution here, which is this y equals -1 line, right? But what changes is the radius, right? Just take y values. If I drew a cylinder, right, if I drew a cylinder here, three-dimensionally, if I rotate this thing, notice here the radius would be 3, from 0 to 3. That's it. Right? The problem is now, look, if that cylinder had to go around -1, and it was that, right? Well, now it would be 4. Why? Because 3 minus -1 is 4. So you see that subtraction of the line we're revolving around. That's a really key component of our setup, and that's what we're going to do in the next problem. All right? So let's talk about how we handle that. Everything that we started with is the same. Pi 0 to 3 over 2, no difference there, right? Yes, it's still dx, nothing, no difference there. But the difference now is when I go to write my outer radius, I need to understand that it is, yes, it's the farther curve, but it's the farther curve minus the line I'm revolving around. So the way I'm going to write that is, I'm just going to look at this change here. I'm just going to have g of x minus -1. That's me accounting for that line we're revolving around. Same thing for the inner radius, right? So now I'm going to do the same thing here, f of x minus -1. And that's the real big change to the setup, right? Now, one other change that could happen, right? Let's go to the other side, right? The top of those curves. So now we're going to rotate around the line y equals 8. So here's just a quick reminder of what the graph looked like. So we had the parabola here, we had the line there, right? But now, think about it. Now, if y equals 8 is up here, what changes? The boundaries don't change, still 0 to 3/2, but what changes is the outer and the inner, right? The outer curve, outer radius, right? The curve would be the farthest away from 8 is now the parabola. That's an adjustment, that's a switch from what we had in the other two. So that's really the only other adjustment we would need to make here. So again, volume, pi, 0 to 3 over 2, all right? But now again, outer radius comes first. So outer radius here is the parabola, right? And so that was really f of x. So f of x minus 8, we're still subtracting that line of revolution, right? And then we can go to inner radius this time, which is g. So I just wanted to make sure we saw some different options there when we're talking about the washer method. In the next video, we'll look at basically the same idea, same problem, but what happens if we're doing a vertical axis of revolution. So I hope this has been helpful. Good luck.